session where many of the participants are online, so therefore like we are conducting it in a hybrid mode so that everyone can benefit from it, and these recordings are also available for later usage. So today there is going to be a lab demonstration session. So this is a lab demonstration session. And we are primarily interested today in knowing about a technique known as the technique that we are going to demonstrate today is known as pulsed laser deposition. So before we get into the details of what this technique is all about, it is important to know some of the applications of this technique. So where all these films are basically utilized, like this pulse laser deposition grown films, like they are like used for making devices to begin with, devices of all kinds. So wherever, say, all of us are aware of devices which are made on silicon as a substrate, following the process steps of lithography and eventually the ultra large scale integration, like which is kind of powering most of our uh, electronics, right? However, like eventually we have arrived in a situation or a kind of bottleneck where silicon based devices will not be able to sustain the kind of growth that we have been following. Say, if we assume Moore's law of doubling of number of say units on a, or number of IC, number of components or number of functional parts in a chip, right, every 1.5 year, if we believe that. So there are already limitations because of limitations on how thin a dielectric could be, how thin a dielectric material could be, because silicon dioxide is the most convenient dielectric material which is used in silicon based technologies, and that kind of has its own limitation. We have almost reached, say, 2 layers or 3 layers of silicon dioxide grown for a technology like a 4 nanometer technology that we see in M2 chips. Right. So let me just close a window. I hope that the noise from these grass cutters will be a little minimized. Give me 10 seconds. I will be back. So these grass cutters decided that they have to compete with me. And as soon as I begin this session, they also have to do, they're doing a fantastic job of landscaping the campus, and in essentially extended monsoon, the campus is really beautiful. So I can bet all of you are missing, those who have not come offline, you are missing a very wonderful environment inside campus. But anyway, getting back to the idea. So silicon technology has really reached bottlenecks, and one of the bottlenecks being the thickness of the dielectric layer. So therefore, high dielectric constant materials are required so that even with slightly thicker film, you can have a similar kind of a task, right? And then there, for that reason, we have to move beyond silicon dioxide. So therefore, pulse laser deposition is one technique which allows you to make other oxide based dielectric materials. So that is one of the things, one of the applications. The other application, if we say from material science perspective, is if we have multi-component materials. right? These multi-component materials are best made using pulse laser deposition. So our techniques of evaporation or sputtering or molecular beam epitaxy and so on, they are most suitable for single component, two component, maybe at most three component. If you are really sure about maintaining stoichiometry, maintaining epitaxy. So however, occasionally by the demand of the physics that we are putting in, we require at least 4 to 5 components that will together form a particular film. I can give an example. Say, for example, let me talk of a material which is a colossal magnetoresistive material, and that has a general formula. This kind of a thing, right? And not only that, in order to further improve this, right, further improve this system, like people also come up with things like, say, they will have a other rare earth. So this is y, this is 1 minus x minus y, and then they have a CaX MnO3. So already you see that there are now 5 different elements which have to be really grown in stoichiometry, right? Stoichiometry. So therefore, for such multi-component materials, like again, pulse laser deposition is one of the kind of chosen technique. Third one, which is very surprising. So like many of you will feel that, oh wow, so this pulse laser deposition is also used in this area. So when we are talking of dental implants, so certain high strength materials which are forming the top layer of dental implants, they are better grown using, so they are again multi-component materials, and they are better grown using pulse laser deposition. So in fact, like this is something which industry has adopted. So therefore, there are very many interesting applications. And as I showed example of a multi-component material, like you are aware of interesting phenomena like multiferroic behavior. So if we want to apply a multiferroic material in a device, then I need to make it in the form of a film. And in such a situation, pulse laser deposition is one of the techniques which really comes to our rescue. So now let me quickly come to what really is being done in a pulse laser deposition technique. So let me see if I can draw, yeah, I can draw a circle, yeah, much more easily. So to begin with, what I have drawn is kind of signifying the cross section of a chamber. Okay, so basically what we are talking of is this is a high vacuum chamber. In another 15 minutes, you will see 10 to 15 minutes, you will actually see what we are talking about. So however, before we get on to that, it is important to know like what we are talking about. And then there would be a direction of incidence of a laser. So therefore, there would be a direction in which laser will arrive in pulses. So a typical pulse width here would be about 6 to 10 nanosecond. So it's really a very small pulse width, right, for the laser. And this is arriving from one direction. So in order to really kind of allow it inside the chamber, we will have ports. Okay, so these ports will be transparent to the laser, incoming laser. So therefore, this would be some kind of a toughened glass through which the laser pulse could get inside. Right. So that's the first ingredient for a for the design of a pulse laser deposition system. So you require a chamber and you require port for the laser to enter. Not only that, this chamber has to be evacuated. So typically in drawing or in schematic, we explain so two vacuum pump. What kind of vacuum pump we will see today in the lab. So primarily one of the possible choices is having a turbomolecular pump backed by a say a rotary pump or a scroll pump. So that really allows you to achieve very high vacuum. Why high vacuum? Because initially you need to clean the inside of the system of any impurities. So now when we are when we have this vacuum pump, we can evacuate to very high vacuums. But then we also need to allow, so there would be a gas inlet through a mass flow controller. Okay, MFC is a mass flow controller. So typically, suppose we are depositing a film which is an oxide. So this gas could be an oxygen gas. Right. Suppose we are growing a multi-component material which is non-oxide. In that case, this could be argon, an inert gas atmosphere. Why a gas is required? Because primarily this pulse of the laser is going to travel all the way. So let me just try to trace the path of the pulse of the laser. So laser is going to travel, and then you will have a polycrystalline metal target. So let's call this a material target. And this target material would be connected in such a manner that it could be rotated or rastered. The reason being, if the laser spot is falling on the same spot of a material, right, it will create color centers and eventually the material could degrade. Plus this is very high energy deposition. So we'll come to some of these details. So therefore, like this target carousel, so this is basically a carousel. So it will kind of rotate the target, right? And it is made in such a way that this assembly does not disturb the vacuum or the partial pressure environment of oxygen or argon that we make. So this is supposed to be leak tight per se, this carousel mechanism. So that's kind of an engineering challenge, but it is achievable. So that is one thing. And then why do we require air or argon, say oxygen or argon? Because eventually when this high energy laser pulse is falling on the material, so from the epi layer, from the top layer, stuff would be ablated out. So suppose I simply provide heat to a target, then we know that atom by atom or like very thin layer by layer, there would be evaporation. But suppose I want an entire chunk to be removed. So here what I decide is, instead of uh, like say very thin layer, I want some kind of a chunk to be removed. Okay, so why chunk? Because it will have about 30 to 40 unit cells of this particular material, target material. And then we will have significant amount of atoms of all the 4 or 5 varieties of elements which we are using. Say if it was an evaporator, if it was an evaporation process, then only atoms on top will be evaporated, and then depending on the saturation vapor pressure, different atoms would not have deposited in the same stoichiometry. So because of that, what we do is we try to ablate out. So the process is called, so laser moves in this direction. Laser moves in this direction, and there is something known as ablation which happens. So ablation is different from what we know as evaporation, in the sense that a larger chunk is basically eliminated from the target. Maybe instead of the top layer, we have about 10 unit cell or 20 unit cell. So the laser pulse is going to penetrate up to a particular depth in the material and then ablate out all the stuff. And this will require to be striking with the air molecules present in partial pressure to form the plasma plume. And the environment is just right such that you can have a kind of assembly on which a substrate is placed. So this would be called the substrate, right? And at times it is preferable to put the substrate on top of a heater. So heater is about, it can go up to 800 degrees C or about 1000 Kelvin. So that sort of creates the right kind of environment for formation of film on top of the substrate. So basically the laser pulse travels all the way. So suppose I design a pulse. So let me just draw it again. So I have a single pulse, right? So a pulse kind of travels all the way, hits the target, right? And then a plasma plume is formed. So this is called a plume, right? A plasma plume is formed, and then that plasma plume will deposit on the substrate, and that's how the film is formed. So now, in order to do this entire process, you will need additional viewports because you also want to see, right, how the process is going on. You would like monitoring this process. So you may have additional viewports, right? Not only on the sides, but maybe also on the top, which I am not drawing. In addition to that, you may have arrangement of determining the thickness of the film which is grown. So many of the pulse laser deposition system come with a facility known as REED. So RHEED. So this is basically an electron diffraction type of a approach to estimate layer by layer growth of the film on top of the substrate. So this is primarily what I wanted to convey for, regarding the PLD. So there are few more small points. So there is something known as the spot size, right? There is something which we already talked of. So pulse width, and then there is energy density. So energy density in say joule per centimeter square. The spot size would be in say millimeter square, and this pulse width would be in nanosecond. It should be a small s, yeah, in nanosecond. So now when I say energy density, so typically for the laser we are using either say higher harmonic ND Yag laser, or One can also use excimer laser. So the whole idea is that it should be a UV laser. Okay, that is important because otherwise the process would be very slow. Like it would not be sufficient amount of energy for ablation, right? So therefore, like you require a Nd:YAG laser or an excimer laser, and this energy density primarily talks about, so whenever this laser pulse falls on the material target, there is a spot size which is created. So we basically measure the spot size, and then we have a thermopile sensor. So under identical conditions, we'll put a thermopile sensor in the place of the material target and measure the amount of energy deposited. Suppose the amount of energy deposited is like 80 millijoule, right? So then 80 millijoule over say zero point 0.1 centimeter square, right, would be like 8 joule per centimeter square kind of an energy. So in general, like the typical energy densities would lie in the range of 1.5 to 3 in units of joules per centimeter square, right? Spot size would be a fraction of a millimeter square, and pulse width, as I already said, it's about 6 to 10 nanosecond, and there is a rep rate, so repetition rate of these pulses of these lasers, and that typically is about 10 hertz, but it could be in the range of 1 to 10 hertz. So every second there could be 10 pulses falling on the material, or every second there could be only one pulse or anything in between falling on the material. So using this, you can sort of estimate, suppose we know the energy density, say the energy density is about, so let's take an example. Say energy density is about, say, how much? 2 joules per centimeter square. And suppose the spot size is, say, 1 millimeter square. So 1 millimeter square would be 0.01 centimeter square. And then suppose we are assuming that the rep rate is only repetition rate is only, say, 1 hertz, right, at the moment. And we know that the pulse width is somewhere between 6 to 10 nanosecond. Let us imagine the largest pulse width. In fact, it could be much smaller than this. So suppose the pulse width is 10 nanoseconds. So basically what happens is, if the energy density is 2 joule per centimeter square and the spot size is 0.01 centimeter square, so amount of energy deposited per spot in 1 second. So energy deposited per spot or per pulse, sorry, per pulse is how much? We can say it is 2 into 0.01, that many joules, right? And therefore the wattage that is seen, or the power of the process, is about 2 into 0.01 in divided by 10 into 10 to the power minus 9 joule per second. So this much watt. So we can quickly do this algebra. So minus 8 here, minus 2. So 2 into 10 to the power 6. So this is like 2 megawatt. Right? I think I have done the algebra fine. Huh? So 2 megawatt. So you can understand, like this is like a entire power plant, like the power of an entire 2 megawatt power plant deposited in a single pulse to the material. So it is a very high power process. Okay, so this is something which I wanted to emphasize. And because of that, plasma is formed inside the chamber. And then if we maintain the temperature of the substrate appropriate, we are really preparing the right kind of conditions under which material will grow in a stoichiometric proportion. Fine, so this is what it is. So as I unshare the slide, I would request Indranil to share the slide so that share this video so that we can switch to the actual lab.
Yes, sir, I am doing so.
Indranil, I hope whatever I said was understandable and audible and understandable.
Yes, sir.
Yeah, okay. Karuna, you were a student of this lab, so now you are teaching in an engineering college. Was it okay? Whatever I explained, was it fine? Yes, you would like to add something? No, sir. Everything is okay, sir. Yeah, Dr. Pradhan, there is a lot of noise coming from your end. If you want to ask a question, please go ahead. Yeah. Indranil, can you share the lab video now? Like direct beaming.
Sir, I have shared already. Is it visible? Like, okay. Yeah, now is it visible?
Not yet.
Okay, let me reshare it.
We just tried sharing just before the session, right? So it should work. Nothing has changed at this end.
No, sir. I have shared using this only.
What you can
By
do
the
is
sharing
you
screen and
can
then
see what you can do, Indranil, is simply unjoin and join again in case there is an issue.
okay.
Okay, you can leave and join back. In between, let me see if there are any questions. So particularly explain stuff which are being done in lab in an online mode is one of the biggest challenges as a teacher. Right, and all of you are teachers, so you can put yourself in the shoe of the teacher who is trying to explain all this in an online mode. Yeah. So this has been really a very nice audience. They have like maintained the quorum, but there are not many questions coming, which I am a little worried. So in the end, we can share it and then you can use the full screen, tap on the full and make it into landscape.
It was done.
And landscape.
Yeah.
Now just tilt the camera.
Yeah. So I have done actually. I think some network issue is there. So
yeah, fine. It is done. It is done. So now you can go ahead and start explaining each of the parts one by one. So starting with the chamber, the laser, the pumping assembly, which is inside this box, right? To the target carousel system, the viewports, the gas assembly, right? Gas line, like everything. If you can go closer, first give a bird's eye view of the entire setup and then you can go closer.
Yes.
Yeah.
Yes, the entire setup view is like that. Like this is the vacuum chamber with target and substrate holders also, and this is the laser system which we'll use for deposition.
Can
The
you
upper
pan a
one is
little
the
above?
AD.
Can you pan a little above? Part of the chamber is going out of the screen. Right.
Okay, yeah, total view will be like that.
Yes. Yes. Yes.
Yeah, yeah, like that. This is the main chamber where the deposition is will happen. The
Uh,
uh, the round circular chamber is this, and
So while
spherical
you
chamber you
speak,
can
maybe
say.
you
And
go in front of the camera and request Ankush to hold the camera. Yeah,
yes,
and
yes.
you can speak a little
Uh,
louder, so that would be yes.
yes, sir. So, am I audible now? Uh,
Yes, you are audible.
yes. So, this is the chamber, and Ankush, can you zoom there inside this chamber? Here you can say this is the target holder. It is okay, okay. So there is a small issue.
Yes, yes, that is fine. It was visible.
Yeah. So I can rotate this target holder carousel. So it is
So
the thing
basically,
which sir have
what
already explained.
Indranil is showing is on the left hand side you have a target holder, right? Top of the left hand
Yes.
side. So if
That,
I use the
that is.
screen, I don't know how I can I annotate? Maybe I can annotate. Right now I am unable to annotate. Okay, so inside the circular part on the left hand side, you can see like three kind of protruding cylinders. So they are basically target holders. And on the right hand side, you have the substrate holder, like which is also the heater. So right hand side, the big cylinder is the heater. And you can also see a substrate which is pasted using silver paste.
Yes, sir.
So this silver paste is something which will survive at about 800 degrees C without really degrading. So this is the inside of the chamber. Fine. Indranil, this is good.
Yes,
So
sir.
this much is fine for the inside. I think
Huh.
everyone is getting a view. Huh? Now you can
Yes.
show like where the gate valve is located. So what is the task of the gate valve?
Uh,
And below that, how the pumping assemblies are connected. Yeah.
yeah. So from the chamber here you can see it is the chamber, and we have just placed some aluminum foil not to mix. If the material chunk is removed, then it should not go through the vacuum. That's why we have placed a small foil only. And up, below that, the turbo molecular pump channel has been started. And you can see here it is the thermomolecular pump setup, or you can say the stage, which was below this box actually. This box,
Mhm.
like yeah, this box.
Yeah.
But this is the stage which were involved, and it is this double stage thermomolecular pump. And then this is the vent where we can purge the outside environment air through that. And this is also a vent. By opening it, we can also purge gas to this roughing valve section, roughing stage section. And it is the valve by which we can close or open the chamber. And this is you can see this is the vacuum controller system, and it was very simpler to handle it by only changing the switching it's only changing the switches and changing the commands. We can do that. And it is the gauge meter. You can see here is the current pressure. Lowest pressure is 8.8 into 10 to the power minus 6 millibar. And this is for the penning gauge channel, and the Pirani gauge channel is showing this much pressure because its capability is of at that time is right this much 4.1 and 4 into 10 to the power minus 2 millibar. It can show up to that. And then it is a gas flow meter by through which we can control the uh, oxygen gas input, or if you can use argon, then it will control the gas flow actually. And then there is the roughing valve, which is nothing but a rotary valve by which we can do rough vacuum of the order of 10 to the power minus 3. Here you can see not 10 to the power minus 3, but below that up to 4 into 10 to the power minus 2 we can see, but it can do up to that minus 2 type of 2 millibar type of things. So below 1 into 10 to the power minus 3 millibar. And this is the setup. It is the PID controller of the substrate heating system. So we can on this. Yeah, you can see this is the main, this PID controller. We can give the temperature at our will. Like if there we need some ramping of the temperature from you can say from T1 to T2, we need some time to stay the temperature. Then again we can increase from T2 to T3 or T3 to T4, and then we can also decrease. So this type of operation we can do by using this PID controller. And this is the heater. We have to synchronize these two things, like this PID controller and the heater. And here you can see the set temperature in green light, and by the red annotation you can see the original temperature. When we on the process of substrate heating, then you can see. But today as the substrate heating for the process is needed a large time, because we can do this substrate heating very controlled manner, in a very controlled manner. So like 2 degree or 3 degree per minute we can increase the temperature. So up to increase the temperature up to 800 or 900, we need a very large time. So we'll not do that part. But I can show you how we can control the PID controller without heating it, but we can do that part. Then the heater will heat according to the PID controller. So sir, this part is covered, and then the laser part have to be. Hello?
Yeah, please go ahead. Please go ahead. Yeah, you can go to the
Yeah,
laser part. Yeah.
yeah. So this is the laser part, where it is the chiller of the laser, because laser
Power supply,
the optical pumping.
come chiller, right? Everything in a
Yeah,
compact
sir.
unit. Yeah.
Yeah, in a compact unit. And the power supply also connected to a constant power supply source, which kept behind the system. And it is a 3 kVA power constant power supply unit, and through which the line was actually connected, this line. And
So you
so
can
this
show
is
the
actually
laser head
connected to
right
the.
now. Right now, it is not showing anywhere. Yeah, you can show the laser head.
Okay, okay, this is the laser head, and it is, we can open
Yeah.
this for yeah. Ankush, come here. Yeah, through that window the laser will come and it will fall on this lens, and after collimation it will hit the target. And I will show okay, yeah, again. So I will show the total
So
process of deposition after that.
Indranil made a very important point. So Indranil, can you focus on the lens part? Okay, we
Yes,
talked
sir.
about the spot
Sir.
size, right? So you can see that
Exactly, sir.
right before entering the chamber, there is a lens assembly. So this is
Mm.
based on HR optics, like basically of material which can really tolerate such high energy laser beams without degrading or without developing color centers. And this is a converging lens. So what really it does is it helps in reducing the spot size. And as we saw, Smaller the spot size, it means more of energy is deposited in a very small region. So accordingly, the wattage increases. So therefore, this converging lens plays a very, very important role. The other thing which you would have observed is there is a reasonably large gap between the air gap between the laser and the chamber. So this large air gap is particularly very much required when we are using an ND-arc laser at higher harmonic. Because in such situations, what happens is this Gaussian beam profile, right, uh, is much more uniform as it travels through some amount of distance. So if it was very close, then we would have from pulse to pulse variation would have been larger. So in order to avoid that, like the laser pulses are allowed to travel some distance in air. This lacuna could be kind of avoided in excimer laser. The distances could be slightly smaller, but even over there, you require laser pulses to travel in air for a while. Yeah, yeah. So Indranil, please go ahead. Sorry for the interjection. Yeah.
Yes, sir. Yeah. Then, sir, it is very beautiful explanation. So it is needed, I think. So this is the this is the rotation controller of the target carousel. We can do actually. I'll do the whole process after that. After showing the instrumentation, and all the process have to be will be discussed after that. So I have just shown that only for convenience. And then you can also see the UPS supply which were kept for the constant power supply to the laser. So this is the constant UPS power supply. So all the instrumentation part have been shown to you. After that, only one part has left. So this is the controller of the laser. So and also the chiller. It was very compact. It is very compact system. So by this system on, we can on the setup, and after that by pump on, you can see the red light spot is there. So it is on. So pump on means the chiller is on. So when the chiller is on, the water will be circulated through the laser surrounding the laser assembly to make it cool. So here you can also see the laser is off now. So as we have already circulated the air means for a very long time, so it's fine now to start the laser, because we need some time to pump the laser means to pump the atoms to its metastable state for a laser assembly, which is known as optical pumping. So we will give this much time, like 15 or 20 minutes, to pump the electron at its metastable state. So you can see when I have on switched on the laser on, the light has already stopped and the on light has been shown there, and then the emission light has here it is already so it is 15 to 20 minutes. I'll start the deposition and how the deposition will take place will show after that. Okay, I have to stop sharing, right? Yes, sir. I have stopped the video for now.
Right.
I need some
Right.
time to be ready, means for the laser to be ready. And in the
Okay.
meantime,
Okay.
I can discuss some slides for that.
Right.
Can
So
I?
no, can you just put the slide, but you want to be ready in the sense you will do few things, or will Ankush help you?
No, sir. Means laser will take time up to 15 minutes. Then
I see, I see.
for
So
the
you can
optical
go ahead with
pumping.
the, fine, fine. So we planned some PPT. You can go ahead. A repetition is better. and it is in a more organized
Yes, sir.
fashion than my writing on a page. So that would help. Yeah, please go ahead.
Yes, sir. I will just yes, demonstrate uh, superficially, we can say. Yeah, I think it is visible. Uh, yeah, I think it is in full screen mode now. Sir, is it fine to continue after that?
Yeah, please go ahead. Please go ahead.
Yeah. So this is the demonstration, and for that I have we have just some contents of thin film deposition and pulse laser deposition, where we'll discuss. We have already discussed the experimental setup, but I will show the main thing. We'll be running of the instrument by step, and then merits and demerits for the pulse laser deposition, and if the other opportunity for the future device experience you can see. So here with thin film deposition, you can see it is nothing but like here we are actually discussing the vapor deposition techniques only, or the plasma deposition. Other deposition techniques like spin coating, drop cast, or Langmuir Blazet thin film coating, those are also thin film deposition technique. But here we are already discussing this physical vapor deposition and chemical vapor deposition. So it is the transfer of atoms from a target to a substrate through vapor or plasma. Vapor you can see from chemical vapor deposition or other thermal evaporation or electric beam evaporation type of techniques. And this plasma deposition will be shown in PLD or in sputtering also, you can see that. So this is PVD and CVD. Both type can be here. But when we need some epitaxial or uniform thin film with proper stoichiometric ratio, and then we have to give the atoms some energy for their momentary transformation from one place to another to sit on a suitable site. Or we can do other thing like substrate heating, which we'll do in a laser setup or sputtering setup also, or any other deposition system. We can do that, the substrate heating part, by which we can thermally agitate the atoms at the face of the substrate to find its suitable site. So you can see this is the chemical vapor deposition process, a schematic diagram of chemical vapor deposition. Here the main difference with physical vapor deposition is nothing but we need some substrate which will react catalytically to form this type of thin film. Or here actually for CNT it was shown, but for thin film also this substrate phase will be reactive to the deposited gas, which will or deposited target material. So this is the main difference between some PVD and CVD. And here are the process of this physical vapor deposition. It is nothing but sputtering, where the argon or inert atoms will bombard to the target, and the target atoms will get deposited at the substrate site. And here it is showing the thermal evaporation by vapor formation using thermal heating, and the vapor will be deposited on the substrate material. And for the PLD, sir has already discussed the process very beautifully. And then after that, this is the schematics which was already discussed, and it is some pictures of our system which was already shown in the video. So this is the vacuum state what we have mentioned already, vacuum state. And behind that the roughing pump is present. So it was not shown here, but the rotary vane pump is behind that. So this is the vacuum stage, and then by zooming the inside the vacuum chamber, you can see the target holder, and already some targets were already pasted here, and it is the substrate holder with with the heater arrangement also inside it. So already the one substrate is clamped using the clamping of the substrate holder, and then you can see the total bird's eye view of this um, total system. And here is the gas cylinder by which the O2 gas will be from which the O2 gas will be in, insert into the chamber, and this is the air laser, and this is the chiller. So after that, I'll discuss actually the main running the instrument, which will be the which process have to be done step by step. So at first, we have means for a vacuum chamber, we must have to maintain the vacuum inside the chamber for all the time. That's why at any stage the chamber will be in vacuum by running continuous, not continuously, but very thoroughly, you can say. We can we have to um, place means we have to maintain the vacuum of the chamber. So when we have to do a new deposition with new target material, we have to vent the chamber first by opening the substrate stage, which was already shown to you. And I will again show you the substrate stage when we'll deposit the sample. And then we will clamp or silver paste. Using silver paste, we will paste the clean substrate at the head of the substrate, which is also a heating element. Then we'll attach the target on the target holder with some tape. Here we are using carbon tape, and then we have to fix it. After that, we'll close the substrate stage. Then the chamber is closed actually. After that, we'll open the valve to connect the chamber with vacuum stage, like thermomolecular pump and this roughing pump stage. We have to connect the chamber. Then we'll turn on the backing pump. Here it is rotary pump. We can also use dry scroll or other pumps. So it is fine. Then we have to turn on fast. Then after that, when the pressure reaches up to 10 to the minus 3 millibar, we will switch on the turbomolecular pump. So as it is a stage 2 double stage turbomolecular pump, so at first it will attend to its stage 1. After attending to its stage 1, then we'll turn on the stage 2. So after reaching the max speed of the first stage of this TMP, we'll switch on for the stage 2. The max speed of the thermomolecular pump is 50,000 RPM, which was used here. So then after obtaining the ultra high vacuum, which is the order of 10 to the minus 6 millibar, we'll turn on the heater, because below that, if we turn on due to some degassing process, the vacuum will degrade again. That's why we need some time to obtain this UHV. So that's why we are turning on the heater after that. Also, you can do at your will, like so before some time also we can do that, but it is not good for the longevity of this system. So so after that, we'll we'll turn off the stage 2 of the turbomolecular pump again, and it will attend to stage 1 before deposition, because if the stage 2 is on, the vacuum will be very high and we cannot control the O2 gas pressure by this gas flow meter for a sustainable time, or you can say for a long time. And then the other processes are, we have to turn on the chiller, which we have already done, and then the laser have to be turned on for the optical pumping, which already we have already done in front of you. And then after some time, the optical pumping was happened. Then we have to fix the rotation of the target, because the target rotation can be fixed from 0 to 360 degree. Which target we have to ablate, we have to fix by this rotation of the target by the rotation controller, and then open the valve for the gas flow. If some gas flow is needed from this to maintain the stoichiometric ratio of this oxide material. Here we are actually depositing oxide now, and if you want to deposit other materials, we can also do using the argon gas flow. Mm, Then we have to, then the laser is ready after optical pumping. The rotation was fixed. Then we'll on the target, we'll on the button there in the target rotation in the controller. Then the target will rotate at our fixed angle, and then we'll open the shutter. By opening the shutter, 10 hertz pulse of this NDVAC laser will be spotted upon this target, our required target. Then the plasma film will be formed, and after that it will be deposited to the substrate. And then after deposition, we have to close the shutter and close the required items like motor pump and the gas flow. All the things we have to close. Then you can say the deposition is complete. So after that, there are some merits and demerits of this PLD setup. So it is very flexible and easy to implement, because also we can make growth of the thin film at any environment, like using any type of gas. You can do that, but usually we are doing here the oxide materials thin film deposition. And exact transfer of complicated materials, as Sarah already discussed, that not only vapor, the chunk type of deposition can be done. So for a suitable chunk, the stoichiometry will be maintained very continuously, and like that, using this PLD setup, YBCO type very
So
complicated
Indranil, a
material can
fine
be
point
deposited.
here. Indranil, sorry, a
Yes,
small
sir.
point here. So when I said a
Yes, sir.
chunk is ablated, I meant a significant part of the, like say, instead of only the top layer of the target, which may
Uh-huh.
have only
Yes,
atoms
sir.
higher in percentage, right, compared to
Mm-hmm.
the other atoms within the unit cell,
Exactly, sir.
right? So when we say a
Exactly.
chunk is ablated, so there is a higher chance of statistically having atoms in the right stoichiometry. So that is at the crux of the success of multi-component film growth using PLD. Yeah. Okay,
Sure,
please
sir.
continue.
Yes, sir.
Thank you. Yeah.
Yes. Then variable growth rate can be done through the controller of the. We can control the repetition rate. We can control the energy fluence and the other parameters which was already mentioned. And the epitaxy can be achievable at lower temperature also, and controlled growth can be done. So we can also manipulate by changing the laser parameter of manipulate the material, like when the target is some metal but we need some oxide deposition, so we just flow the oxygen gas and maintain the required pressure, or you can say not required but the controlled pressure, and then we can do optimized pressure we have to maintain. And after that, if we do the PLD, and then we can find the oxide also. So your target is metal, but we can deposit oxide by this oxygen environment creation. So this is again the point is new material synthesis opportunity is there due to this type of synthesis techniques. And the demerits are here, like if the substrate size is large compared to like 1 centimeter cross 1 centimeter is fine, but after that if we do, then you can see at a central point the deposition is highest, and when we are going to the edges, then the means of deposition of the material will be lower compared to the central point. So this type of uneven coverage will be there because it is very localized. So the deposition will not be for a very large scale. So it is not well suited for the large scale film growth. And if we don't have the optimized oxygen pressure, inside the chamber, then this is very probable to have this high defect and particulate concentration. It is a very common problem for PLD techniques, and whatever mechanism and parameter dependence are involved, we can achieve those experimentally, but the theory for this tuning is not very well understood till now. So some also it is a demerit, but again it will be a merit because this is an open space. You can do uh, theoretical study for that also. So opportunity, we can mention that if we have some very small circuit design, and by using proper masking, we can do that circuit writing, because due to this localized deposition. And what we have already mentioned, that new materials can be found using the tunable parameter change inside the inside the vacuum chamber. And nanoparticle production is a very important thing. You can use, if like the in the face of the substrate, actually the deposited particles are of the order of nano range. So by every pulse there is a layer of nanoparticles which are depositing in the substrate. So nanoparticle production can be done uh, through this pulse laser deposition. Here you can see by changing the parameter, the tuned parameter is only the oxygen partial pressure inside the chamber, and you can see uh, the plume evolution or plume shape of this plasma plume is very much affected by this um, uh, inside oxygen pressure atmosphere. So that's why I have given the picture for that, and it can give you the sense how much thick thick film you can get by this type of plumes. Like when we are varying this oxygen pressure, then you can see the plume shape is very much wave front of this space, or you can say plume, are different for different pressure. So different type of growth will be formed by this tuning of this oxygen pressure. Uh, it is all of that I have prepared for this.
Are there questions? Please go ahead. So Indranil, I would request you to share the kind of video of the what do you say? Yeah, once more, like the image of
Yes, sir.
the PLD once more. We'll just take a snapshot, and I request other participants to please switch on your cameras.
Yes.
All the FDP participants,
Sir, is
please
it
switch on your
fine?
camera. No, this is not fine. Do it in the landscape mode. So 100% and landscape.
Uh, Sir,
See, the rules remain the same, right?
okay, sir.
Yeah, I request other participants also to switch on their like videos. Yeah, okay. So please, if you can switch on, yeah, we will be seeing you also there. Yeah, thank you. So right now the video is not visible. It's darkened. So fine. Thank you. So fine, Indranil, this is, I think this is okay. So are there questions from the participants? Thank you for switching on the videos. Now maybe you can switch them off. Yeah. So are there questions? Are there questions? No. Okay, so I would again request request all of you that the next session would be at 7 p.m. So I request everyone to join for that session. Today, Professor Manoranjan Kar will be talking about a lot of interesting stuff. Thank you so much. So maybe we'll close this session now.